Hey everyone, my name is Jamie from UC Berkeley's PEACE Tutoring organization, and today we will be going over probability and conditional probability. First, we'll talk about probability and go over a few examples. Then we'll dive into set theory because I think set theory is a good way to think about probability. And then we'll move on to conditional probability and the difference between dependence and independence. Afterwards, we'll talk a little bit about the addition rule, and finally, mutual exclusivity versus independence. And there will be a problem at the end of this whole thing, which you can try out on your own. Another term for probability is just chance. What is the chance of it raining today, or what is the probability of a flush in poker? But probability is just how likely an event will occur, and that's calculated by the number of ways of an event occurring over the total number of possible outcomes. So let's dive right into an example. Suppose I have a standard 52 deck of cards, and I pull 2 cards off the top of the deck. What is the chance that your first card is a spade? This seems pretty intuitive. We're just looking for the occurrence of grabbing a spade. You have 13 spades in a deck out of 52 cards total, so the probability of drawing a spade is just 13 over 52. Broken down, that's 1 over 4, or 25%, which makes total sense. Spades make up 1 out of 4 suits in a deck of cards. What if I were to ask you about the probability of the second card being a spade? Now, this is a little tricky. You must look at the question carefully before jumping to any conclusions. I asked about the chances of the second card being a spade, but I didn't tell you anything about what the first card was. So here you must assume that you don't know anything about the first card. So if I just grabbed 2 cards and I didn't know anything about either card, the probability of the one on the right being a spade is the same 13 over 52, or 1 over 4, just like the same probability of the left one being a spade. Now let's look at the probability of both cards being spades. The probability that one of the cards being a spade is the standard 13 over 52, just like you'd expect. But now the probability of your second card being a spade is not 13 over 52 because you turned over your first card and found out that it was a spade. Thus, your chances of the next card being a spade has changed because you removed 1 card from the deck without replacement. If you took out a spade already, the probability of your next card being a spade has changed to 12 spades remaining out of 51 cards remaining in the deck. So now the combined probability of both cards being a spade is your first probability that you got a spade in the first place, 13 over 52, multiplied by the probability of your second card being a spade, given that you already knew the first one was a spade. So that's 13 times 12 over 52 times 51, and that comes out to about 5.9%. That was the probability of both cards being a spade, but what if I ask the question, what is the chance that both cards are of the same suit? Now I'm generalizing the question to be any of the 4 suits. Well, we already found the probability of both cards being of one suit, but there's 4 suits in a deck. So the chance of both being of the same suit is the chance that both of them are spades, or the chance that both of them are clubs, or the chance that both of them are hearts, or the chance that both of them are diamonds. And each one of those has the same exact chance of occurring. By the addition rule, you can just add up all of those probabilities. The probability that both cards are of the same suit is just the number of suits times the chance of both cards being of one of the suits. This is properly written out as 4 choose 1. Out of the 4 suits, you're choosing one of them to be of the same suit. And this 4 choose 1 factor here is a combinatorial component accounting for the unordering of the number of ways that one suit can occur. But just remember that all probability is just the number of ways of your event of interest occurring divided by the total number of possible outcomes. And never forget that probability is always on a frequency scale of 0 to 1 or on a percentage scale of 0% to 100%. And it is never anything less or never anything more. So if you ever come up with a probability that's outside 0 or 100%, then you're doing it wrong. Okay, so now I'll talk about what the difference is between probability and conditional probability. Probability, just like I mentioned before, is the number of occurrences divided by the number of total possible outcomes. But conditional probability is the probability dependent on something else happening. It's the chance of an event occurring given another event already occurred. And whether you know it or not, you actually already have been over an example of conditional probability. Before, when I asked, what is the chance that both cards are spades, the chance of your second card being a spade was dependent on the outcome of your first card. So what if I had asked, what is the chance of your second card being a spade, given you know that your first card is a spade? Well, that's 12 spades remaining out of 51 cards left in the deck. If your first card was not a spade, then your chance of the second card being a spade has changed to 13 over 51. So that's just an example of conditional probability where the occurrence of one event is dependent on the occurrence of another event happening. All right, so I'll talk a little bit about frequency theory. And this is a process that can be repeated over and over again independently. Independence means whatever happens to the first result doesn't affect the next outcome, like flipping a coin or rolling a die, and you normally want each of these trials to happen under the exact same conditions. As an example, if you flip a coin 8 times, you can capture how many times heads came up. And you can do this experiment many times under the same exact conditions to get a sense of the true distribution or the true average of the frequency of heads. So if you repeat this experiment over and over again, the distribution will look like a normal distribution with very nice properties that you can use, like the area under the curve being 1. And then you can use this distribution to do interesting stuff, like find the probability of getting 7 heads or more. This is a really nice property of the normal distribution, which allows you to conclude things very easily. And that's something that's much harder to do with a lot of other types of distributions. Now we will go into set theory. When thinking about probability, I think it's very understandable to put things in a box. This box here represents the total number of possible outcomes, so the area inside the box is 100%. And the space A represents the events that you're looking for, and the area of space A will always be 100% or less. And unless the occurrence of A is the only thing that can happen, then it will usually be a subset of the total space. As an example, let's say that A is the event that you roll a die with 5 spots or less. That means A complement, anything outside of A, is the event that you don't roll 5 spots or less, aka all other possible events within the realm of possibility. So that means the possible outcomes of the event, A rolling 5 or less, is rolling a 1, 2, 3, 4, or 5, which leaves the only other possible outcome to be an A complement, which is rolling a 6. Now let me shift gears into conditional probability. Given that you rolled a 5 or less, what is the probability that you rolled a 2? Now this is slightly more interesting. A conditional probability is written out like this. This says the probability of event A occurring given that event B happens. The bar in between means given in statistics. And the conditional event, in this case B, always comes after the bar. All right, the traditional formula is written out like this. The probability of event A occurring given that event B has occurred is the probability of both event A and B occurring together divided by the probability of event B. This might seem a little weird at first, but let me give an intuitive explanation. You are asking for the probability of event A occurring given that event B has occurred. So if you take a look at the graph, that's essentially saying that you are already in the event space B because you were given that event B has occurred. So by looking only at the blue circle or being in space B, what is the probability that A occurs? A short way to say that is what is the probability of also being in A given that you are already in the blue circle B? Therefore, the chance that A occurs inside of B is the intersection of the area of A and B divided by the area or possibility of being in event B. So back to the dice example. Given that you rolled 5 spots or less, what is the probability that you rolled a 2? The math is written out like this. The probability of rolling a 2 given rolling a 5 or less is equal to the probability of rolling both a 2 and a 5 or less divided by the given condition, the probability of already being in the space 5 or less. Now the numerator might sound a little weird. What does that even mean to have rolled a 2 and rolled a 5 or less? Now imagine the classic Venn diagram like the one pictured on the left. It doesn't really visualize that particular statement. Instead, the event space looks something like this. Rolling a 2 is actually inside the event space of rolling a 5 or less. Thus, really, the probability of rolling a 2 and rolling a 5 or less is the intersection of both conditions, which in this case is just really the probability of rolling a 2. So the chance of rolling a 2, given that you rolled a 5 or less, is the probability of rolling a 2, which is just 1 over 6, divided by the probability that you rolled a 5 or less, 5 over 6, which comes out to 1 in 5. And that answer makes perfect sense because if you already know that you rolled a 5 or less, the probability that you rolled a 2 is just 1 in 5. Again, the equation on the left is the formula for conditional statements. But remember, you can rearrange the equation and solve for the intersection, the probability of A and B occurring instead, which is the chance that A happened given B happened multiplied by the chance of B happening in the first place. And sometimes this and variable is easier to conceptualize or solve for. A quick note about conditionals with independent events versus dependent events. If events A and B are completely independent, meaning that the event of one happening doesn't affect the event of the other happening, like tossing a coin or rolling a die, then you can separate out the probability of A and B occurring to just the chance of A occurring multiplied by the chance of B occurring. Right. The event that B occurs doesn't have any influence on the chance of A occurring. Thus, the chance of A occurring, given that B occurred, is really just the probability of A occurring itself, since they're not really related. If the two events are dependent, or their probability spaces rely on the outcome of the other event, then the chance of A and B both occurring is the probability of A occurring given B happened, multiplied by the probability of B occurring. Or you can say that it's the chance of B occurring given that A happened, multiplied by the chance of A occurring in the first place. As an example of an independent event, it would look something like this. A is the event that I wear green today, and B is the event that it rains today. Obviously, neither of the events affect each other. The chance that it rains today has absolutely no influence on what color I decide to wear, and the probability that I wear green today, given that it rains today, is just the probability of me wearing green today. Again, cards is a great example of a dependent event. If A is the event that my first card is a spade, and B is the event that my second card is a spade, then the probability of my second card being a spade changes based on the outcome of the first card. Now these events are tied, they're dependent. The probability of my second card being a spade, given you already know the outcome of the first card, is the chance that both cards are a spades, or the intersection of both events happening, over the chance that the first card was a spade in the first place. Or maybe the more conceptual one to solve for is what is the probability of both cards being a spade. It's just the probability of the second card being a spade given that the first card is a spade multiplied by the chance of the first card being a spade. Right, so to visualize this and really nail the concept down, if we look at our event space here, the entire box represents all of the possible outcomes of drawing two cards. But we're interested in the cards being spades. So our orange bubble here, A, represents the possible outcomes of the first card being a spade. And the blue bubble represents the events that the second card could be a spade. And the intersection of the two spaces holds all of the possible events in which both cards are spades. So if you were to find out what is the chance of the second card being a spade, given that the first one is all of the events or all of the possible ways in which both cards are spades over the event space in which the first card can be a spade. Remember, when you're going over problems, it's best to translate the question into what you can write out easily in math. When the question asks for both cards being a spade, you should be translating this to the first card being the spade and the second card being a spade. From that statement, it's much cleaner to write out what you want in math. After you do that, you must realize that these events are dependent. They're not independent events. Now you can clearly write out a question in English to a statement in math, and bonus points if you have extra parentheses. And then you can solve the problem. The chance of the first card being a spade is 13 over 52, and the conditional chance of the second card being a spade, given that the first card was a spade, is 12 over 51, which comes out again to 5.9%. Now let's try a slightly harder problem. You randomly select 8 letters from the alphabet with replacement. Given that your selected set has only 3 vowels in it, not including Y, what is the chance that all of them are E's? While using our conditional formula, the probability that all the vowels are E's, given that there are 3 vowels, is the probability that you have 3 vowels and all of them are E's divided by the probability that you have 3 vowels in the first place. The next question that you have to ask is the event of getting an E independent from the event of drawing a vowel. You might initially think that they're independent because you're drawing with replacement. The letter that you grab first doesn't have any influence on the next letter that you grab. But these two events are actually dependent. If you happen to grab an E first, that changes the probability of getting 3 vowels total. And if you grabbed an A first, that changes the chances of having all 3 of them be E's to 0. But you still have to stop and think about what it means to draw 3 E's and only 3 vowels. To find this probability, we have to use what's called the binomial formula. The binomial formula is specifically calculating probabilities of a number of events occurring based on a binary outcome, the number of successes and the number of failures. So here, when we are looking at the probability of 3 E's and 5 consonants, the probability of getting an E is 1 over 26. And since we are looking for 3 E's, the first box is E, and the third box is E, and the sixth box is E, is the chance of all 3 of those boxes being a success together. Thus, you multiply the probabilities together to get a total of 1 over 26 to the third power. And you do the same for failures. If I want 5 consonants or 5 non-vowels in the remaining boxes all at the same time, then we multiply all of those probabilities together to get 21 over 26 to the 5th power. But this answer calculates the exact chance of picking these E's in this particular order. But I don't care about what order I pick the E's in, I just want 3 E's. So we have to tack on an additional term that accounts for all of the possible combinations in which the order of successes came in. Out of 8 spots, I'm choosing 3 boxes to put the successes in, and I'm choosing 5 boxes to put the failures in. So this 8 choose 3 is a combinatorial factor that is an unordering term. It's used to unorder the specific probability that you asked for by accounting for all of the possible combinations of ordering. Now, when you're calculating the denominator, the probability of choosing 3 vowels is the same setup. It's the probability of success, 5 over 26, because there are 5 vowels, and you're picking 3 vowels, so 5 over 26 to the third power. Now, when you put the probabilities together, you have 2 binomial probabilities, many of which the terms cancel out, and you're left with 1 over 5 to the third power. And this makes a lot of sense. Given that you selected 3 vowels, what is the chance that all 3 vowels were E? Well, that's 1 over 5 times 1 over 5 times 1 over 5, or 1 over 5 to the 3rd power. Now we will move on to the addition rule. Because when we calculated anything with an AND statement, we were looking for the intersection between 2 events and multiplied the 2 chances together. But if the question asks for one event or the other event, we are looking at this gray space here, which covers everything in A and everything in B, including the intersection. So the probability of A or B is the probability of A plus the probability of B minus the intersection between A and B. So why did we subtract out the intersection? Well, it's because we double counted that intersection. We counted for A and B once in the space of A and again in the space of B, but we only need one copy of it. So we subtract out that extra double counted term. Here's a very simple example. Taking a card off of the top of a deck of shuffled cards, what is the probability that your card is a 4 or a heart? The probability of grabbing a 4 or a heart is just the probability of grabbing a 4 plus the probability of grabbing a heart minus the probability of grabbing the 4 of hearts. You subtract out the 4 of hearts because you accounted for that particular card in the probability of getting a 4 and in the probability of getting a heart. Right, so that's 4 4s out of 52 cards plus 13 hearts of 52 cards minus 1 4 of hearts over 52. All right, so the last topic that we're going to go through is mutual exclusivity versus independence. Mutual exclusivity means that there's no chance of both events happening together, thus the probability of A and B is 0. For example, if A is the event that my card is a heart and B is the event that my card is a spade, then both of those events can't happen at the same time. Independence is when A and B don't affect each other. Thus, the probability of A and B is the probability of A times the probability of B. Again, if A is the event that it rains today and B is the event that I eat broccoli today, those 2 outcomes don't depend on each other. It's not to say that they can't happen together. Here's a question. Are mutually exclusive events independent? Go ahead and pause the video to give this a thought before proceeding. So if A and B are mutually exclusive, that means that the chance of A and B happening together is 0. Suppose that the probability of A and the probability of B are both greater than 0. That means they have at least one case inside of each of them. If they were independent, that means that the product of the 2 probabilities must be greater than 0. And if they were independent, we can write out the chance of A and B as the chance of A times the chance of B, which should be greater than 0 if independently they're greater than 0. Thus contradicting the first statement of being mutually exclusive, thus A and B are not independent. This also makes sense. If you are in the space of A, you are guaranteeing yourself not to be in the space of B, making A and B related or dependent on each other. All right, that's all I have for my mini lecture in terms of content. Really try to practice and test out your newfound knowledge by trying out this problem to see if you really understand the concept. All right, that's all I have. I hope you found this lecture useful. And a quick thank you to UC Berkeley statistics professor Gaston Sanchez for some of his slides, which are absolutely fantastic. And you can check out his website here. And thank you again to UC Berkeley's PEACE Tutoring program for providing a platform to host educational videos. All right, guys, good luck.